Saxon Advanced Mathematics, lesson 112. Our topic today is Binomial Theorem, which sounds heavy and dull, but I think this lesson is a breath of fresh air. It's an idea whose time has come. You know, we have been working on this idea called binomial expansion. And that is where we've been taking binomials. We call them sometimes a plus b, and we raise them to a power, right? I'm just going to put a power on here. Let's say the fourth power. And we know that we can create that sequence of numbers, right? We can write out the whole expansion, or we can find a particular term by using two tools. The first one is called Pascal's triangle. And that's that thing, I'll show you, remember we do a plus b to the 0 power is 1, and then 1. We're writing a pattern of coefficients, right? And after we get it going, we're just adding the numbers. That gives us, I said this, but I'll write it down too. This gives us the pattern of the coefficients. So that's the first tool that we've used to create the binomial expansion. But then we need to know what exponents go on each term. So then we write another little chart that's called the pattern of exponents. And in those, what we do, like with this one to the fourth term, we would say, okay, first term, second term, third term, fourth term, and we'd say for the a coefficient, it's going to start at 4 and go down. And then for the b coefficient, remember that if we're raising to the fourth power, we actually have 5 terms because there's one term where that's 0, and then the b terms go up, right? And we notice that the total exponents for each term always equal the power that we're raising it to. And this gives us the exponents themselves to put on each term. Okay, so we've used these two tools and we've been successful with it. We've also learned that sometimes if these original terms in the binomial, if they're complicated, what we can do is write this as first plus second to the fourth or whatever, and then we can work out the coefficients and the exponents, and then at the last minute we'll substitute back in the actual values where we put f and s. So f and s, first and second, are a way to simplify the calculations so that we don't lose our mind in details as we're going, because we have a lot going on with this process of binomial expansion that we've been figuring out. And what we've realized is that if you're trying to raise to a super high power, you would have to take Pascal's triangle and blow it out. Possibly, like if you wanted to find something raised to the 51st power, you'd have to do a lot of work to develop the triangle. That's a pain. Pattern of exponents, again, it's not so bad when we have a relatively low number of terms, right? We were raising this to the fourth power, so we had 5 different terms. That's not the end of the world, but what if we want to use bigger numbers? There's got to be a better way. Well, this lesson is about the better way. What we have is a formula, and at first the formula, you're going to go, what in the actual heck am I supposed to do with a frightening formula like this? But once we use it in the 3 examples, I think that what you'll find is, oh, that's actually not bad at all. It makes a lot of sense. All right, so don't worry. If you're horrified at first, I understand. N equals the number of terms. No, I don't want to say it like that. I want to say it's the power of the expansion. Okay, it's the number that we're raising to the power of. Or another way of saying it is it's the exponent All right. K is the term we want. Like most formulas, when you first see this, you're going to go, what? But then it'll make more sense, don't worry. And of course, as we've said before, f is the first term in the binomial. And s equals second term in the binomial. Okay, so are you ready? This is called the Binomial Theorem. It's the name of this lesson. It's the name of this formula. And really all it does is it uses the patterns that we've already seen as we've worked through these binomial expansions using Pascal's triangles and the pattern of coefficients. So this isn't new ways of looking at these numbers. It's just kind of a formula that gets us there faster. That's it. This formula gives us the coefficient, the exponent that goes on the first term, and the exponent that goes on the second term. When you see it written like this, I think you will agree, it looks fairly horrifying, doesn't it? But what we're going to see is that when you actually start to use it, notice that this expression here, the first half of the denominator, is the same as the exponent that goes on the first term. And the second part of the denominator is the exponent that goes on the second term. Oh, that takes a lot of drama out of this when you realize these pieces are the same. When we actually start to use them, I think it'll make sense for you. And in the first problem, John's going to give us a set of numbers where we can do it the old way too, and then we'll use that as a test to see how the new one works. So let's do example 112.1. Okay, get myself back in frame. Find the 8th term of the expansion f plus s to the 12th. All right, so we're not getting anything more complicated. We're just going to stick with f plus s. We're trying to find the 8th term of the 12th power. All right, so using my list, n equals the power of the expansion. So in this one, n equals 12. And k is the term we want. We want the 8th term. Now, this one is easy enough that we can remind ourselves, like I said, we can remind ourselves of doing it the old way. We know that the pattern that we're going to follow, I'm talking about the, let me say this. We know our answer is going to look like this. We're going to have a coefficient. That's what we used to get from Pascal's triangle. We're going to have f to a power, and then we're going to have s to a power. This is what we used to get from what we call the pattern of exponents. Okay, so this is the way we want our answer to look. A coefficient and then 2 exponents on the f and the s. We don't have to worry about more complicated terms there. This problem is easy. Okay, so what I'm talking about is, let's not talk about the coefficient just yet. We would have to make Pascal's triangle. We would have to make all the way to the 12th power. Not gonna happen. That's too much work. Remember, mathematicians are inherently, I don't want to say lazy, but efficient. We don't want to do a bunch of extra work just for the sake of doing it. No, we've got better things to do. But we can easily get to the exponent on the second term by remembering that there's a relationship between that exponent. It's always one less than the number of the term. So if we want to go all the way up to the 8th term, we know that that's going to be 7, right? Because we're following this pattern. The number of the exponent on the second term is always one less than the number of the term itself. So we know that that is going to be 7. Now we also know that the two exponents will always add up to the power of their original expansion, right? We did this before. We looked at the exponents for a power of 4, and here's what we're doing. We copied, right? We start with 0 with the second one. We start high with the first one, but they always add up to 4. So that tells us in our example that these are always going to add up to 12. So this would be 12, and this would be 13, and this would be 11, and then we go dot, dot, dotty. 7 and 4, these all are adding up to 12, right? Oh, wait. What am I doing? There, sorry. My brain went sideways. This adds to 12, this adds to 12. So this is going to have to be 5. We know because this has to add to 12. So this gives us the numbers we need there, right? But let's indulge this binomial theorem thing, and let's try finding them like this. So we would say that f, which we know should have a binomial of 5 on it, is going to be raised to the power of n minus k plus 1. And in our example, that's 12 minus 8 plus 1. 12 minus 8 is 4, plus 1 more is 5. That's f to the 5th power, and that's exactly what we calculated over here. Our s, using the formula, should be equal to k minus 1. And with our formula, k is 8, so it would be 8 minus 1. That gives us 7s to the 7th, and we proved it with our own hand calculation. So these formulas, we can see, do indeed work for this. And I'm not going to go into details of explaining exactly how, but these formulas are simply taking into account the relationship among the numbers that we already know exist, right? We know that for the second one, the exponent is always going to lag behind the number of the term by 1, and we know that the first exponent is going to be whatever it takes to total to 12, or the power that we're raising to. All right, so we have used both the formula and our old pattern of coefficients technology to figure out those exponents, and those are correct. Now, to figure out the coefficient, like I said, we used to use Pascal's triangle. This thing, we do not want to make rows and rows and rows and rows of this. So we are going to trust our binomial theorem, which has already proved itself with the exponents. Now remember what I told you. The exponent of each of these terms are in the denominator as factorials. We take the factorial of both. But we don't have to recalculate these. Now that we've calculated them for these purposes here, I'm going to draw a little box. And this is where we'll do our coefficient. We can use our binomial theorem. Okay, the top is the power we're raising to. And then we use the two exponents we've already calculated, 5 factorial over 7 factorial. Now it feels easier, doesn't it? Because we're not calculating all of these crazy things separately. We do these two, they make sense to us, and we copy them to the bottom. If we do this, I did it by hand and it wasn't hard to simplify this. Remember that, here, I'll do it down here. Remember that the easiest way to simplify something like this is to offset the factorial of the larger number against the top. So I'm going to write it as 12 times 11 times 10 times 9 times 8 times 7 factorial. Then I'll divide by, and I take the smaller number and write that out, 5 times 4 times 3 times 2. I'm not going to write 1, that's not necessarily. Times 7 factorial. Now I can cancel those two against each other. That's why I choose the larger number, because I'd rather cancel as much as possible. 5 times 2, cancel the 10. 4 times 3 cancels the 12. And I'm left with figuring out what's 11 times 72 is how I would do it. And I know the answer is going to look like this, 72, right? If I multiply 72 times 11, this is what I'm going to get. I could put the 0 if I want. And that's going to be 792. So my final answer is a coefficient of 792, f to the 5th, s to the 7th. And that's correct. Yay. Okay, one example. Let's do another one. And this one, John also simplifies the process for us by, sorry, let me catch up. We're to find the 10th term. So that tells us that k equals 10. And our expansion is f plus s to the 14th. And what I was saying is John's giving us a break, and we're not going to substitute anything more complicated in spoilers. We will on the next one. We're just leaving it with the simple f and s. We're raising it to the 14th power, so n equals 14. We don't have to worry about values for f and s because they just are what they are. And so now, again, I'm going to set up my answer. I know I'm going to have a coefficient, and then I'm going to have f to some power, and I'm going to have s to some power. I know that these two are going to have to add up to 14, and I just know, because I understand the way this works, that because I'm trying to find the 10th term, my exponent in here will be 9. It's always one less. But let's look at the formula again for the whole thing. Okay, and just to remind you, this is the coefficient. Oh, I forgot to put the factorial markers in there. Right? All three pieces are factorials. But this first number is the exponent that goes up here. So it's n minus k plus 1. And this one is k minus 1. I'm comfortable guessing that this, if this is 10 terms, then this will be a 9, right? And that makes sense because k minus 1 equals 10 minus 1. So that's 9 here. And we know that they're going to have to add up to 14. So let's try this. N minus k plus 1 equals 14 minus 10 plus 1. 14 minus 10 is 4, plus 1 is 5. So that tells us that this is a 5. They add up to 14. Check, check, and check. This formula really does set us right. Now, this, and these are the exponents, right? Now that we've got our exponents sorted out, it's super easy to set up the coefficient. So that's how I always do it. Do the exponents first, and then once you've got, and that you can double check, right? You can use your common sense checks to make sure that you're in the right ballpark. Then once you get these exponents, it's really easy to set up this coefficient calculation. And I'm gonna do it down here. And it's gonna be 14 factorial over 5 factorial times 9 factorial. All right? The 9 factorials are gonna cancel. I'm gonna set it up that way. 14 times 13 times 12 times 11 times 10 times 9 factorial. I'll write out the 5s. 5 times 4 times 3 times 2 times, I don't need the 1, 9 factorial. These cancel. Let's see, I'll do the 5 and the 2 against the 10 and the 4 and the 3 against the 12. Now I just have to multiply together 14 times 13 times 11. 14 times 13 is 182. And then I know the pattern for multiplying 11. You just take 1 times the number and then 10 times the number and add them together. 2, 0, 0, 2. That's our coefficient. (2002) is our coefficient times f to the 5th, s to the 9th. Done. And that's correct. All right, beautiful. So that's as hard as it gets, almost. Now what we're going to do for our last example is we're going to have more complex terms in our original binomial. We're going to substitute them out, solve all of this using f and s, and then at the very last step, we'll plug in the actual terms for f and s and simplify. John, what do you want from us? Find the 10th term. So I'm not going to write 10th term anymore. I'm just going to write k equals 10. And then I'm going to go right in and find n. That's the power on the expansion, 15. John wants us to find the 10th term, and he writes this as the term. 2x to the third minus y. That's our binomial. It's got the 15 up here. I've already copied that over. So we can see that our value for f is going to be 2x to the third, and our value for s, first and second, is minus y. Okay, let's get our binomial theorem on the page. N minus k plus 1, k minus 1. Those are the exponents. I always write them before I put the factorials in, and then I have to squeeze them in. All right? And then we'll have f to this thing, n minus k plus 1, and we'll have s to this thing, k minus 1. All right? I want to do the exponents first. So this is going to be f to the n. No, I want to do the s first because the s always makes more sense to me. If we're finding the 10th term, then this should be a 9, shouldn't it? It should equal 9 if our logic is working. And this, since they both have to add up to 15, this should be a 6. So let's check it and see. K is 10 minus 1. Yep, sure enough, it equals 9. So I feel very comfortable with that. This, n minus k plus 1, would be 15 minus 10 plus 1. 15 minus 10 is 5, plus 1 is 6. Good. So our guess, no, our mental calculation, it wasn't a guess at all, was it? We used our old information about pattern of exponents, that the second one will always be 1 less than the number of the term, and the first one will be whatever it takes to add to the power. That rule holds. So this is 6. All right, so we've got our exponent straightened out. Now we need our coefficient. N is 15 factorial over, and we've already done these calculations, so it's 6 factorial times 9 factorial. See, this coefficient calculation becomes so easy if you do the other one first. And we use our pre-existing knowledge about what these exponents should be to guide and make sure that our calculations are correct. Then we just copy those over and simplify the factorials. Again, you could use a calculator, but honestly, I would rather you do these in your head. They're not too complicated. So this one, again, we want to cancel the higher of the 2 factorials. 15 times 14 times 13 times 12 times 11 times 10 times 9 factorial, finally. And then 6, 5, 4, 3, 2 times 9 factorial. Cancel, cancel. Now let's see, what can we get rid of? Well, let's just take the 5 and the 2 against the 10. And let's take, well, let's see. Oh, I'm looking at the wrong problem. I was going to say, my numbers aren't working out. I did it differently than before. I'm going to do this because I got to get rid of that 6. The 3 will go against the 15 and I'll have 5 left. And now I've got 4. I'll take 2. I'll split this up into 2 times 2. And I'll take one of the 2's out there, and I'll take the other one there. So now I'm left with, that was crazy canceling. That wasn't the easiest way to do it, but that's what I did, so whatever. Here are the numbers I have left. 7, 13, 5, and 11. 7 times 13 I know is 91, right? It's 21 plus 70, so it's 91. 5 and 11 are 55. So I'm going to multiply this. I like to have the double-digit number down here where they match because that means I'll have the same product twice. 5, 45. Then I'll have it again only with a power of 10 there. That gives me 5. Oh, okay. So that tells me that my coefficient is 5005 f to the 6th, s to the 9th. Okay, that's correct. But in this problem, we have one more step. We have to put in these additional, these more complex values for f and s. Remember last time we didn't have those. So I'm going to take this to the next page. 5005 f to the 6th, s to the 9th, and then I'm going to put in my values for f. F is 2x to the 3rd, and I have to raise that to the 6th power. And then s is minus y, and I have to raise that to the 9th power. Remember, these values came from the original binomial that we got out of the problem. Oh no, I've had a rip there. All right, so this is f and this is s, and I had defined them here, right? 2x cubed minus y. So I'm plugging those values back in. Now I have to simplify them. So my 5005 is just chilling out here by itself. 2 to the 6th. Okay, this is when all my hours of playing the game 2048 come in. We just double up the numbers, right? So 2 to the 1st power is 2, 4, 8, 16, 32, 64. So 2 to the 6th power is 64. And then how do we raise a power to a power? We multiply. So that's 18. Then y minus y to the 9th. Okay, when I raise the minus, you can think of it as a -1 if that helps you, or just the minus sign if that's fine for you. When we raise it 9 powers, 9's an odd number. That means we're going to come back with a negative. And then y to the 9th power is y to the 9th power. All I've done is just brought that power inside to say, okay, this has been simplified. Now we have to do our final calculation. I see that we have a negative sign here, so that's going to carry to the outside. I have to multiply 5,005 times 64. I can put a 0 in there if that helps. 320320. That's an interesting number, right? So it's negative. This, which is what we get when we multiply these two chunks together, x to the 18th, y to the 9th. Our minus sign is already living out here. This is the correct and final answer. Okay? So using the binomial theorem was the same. We just had to take the extra step of plugging back in our value for f and our value for s. We took those out in the early stages of the problem so that we didn't have to deal with their complications. We just calculated the coefficient and the variables that we needed. Then we substituted those values back in, simplified, la-di-da. That is, let me just triple check, 18 and 9. Yes, those are the right answers. Yay! Lesson 112 is completed. We are done through week 29. 8 more lessons to go. Yay! Thank you. Goodbye.